Hello everyone. We're going to start with a new chapter in this video lesson, and in this chapter we're going to look at DC circuits. DC stands for direct current. Don't worry about that. You're going to know what that is in the next few chapters. But in this chapter, you're going to look at the circuit rules. So in the previous chapter, you already learned about the electrical quantities. These are current, voltage, potential difference, electromotive force, and resistance. So if you do not know what those mean, you can go back to the previous video lessons and go through those videos again. This chapter will be divided into 6 to 8 parts depending on how fast we want to go through this chapter. For this first part, we're going to look at series circuit rules. So when it comes to creating circuits, there are certain ways the current, the resistance, and the voltage behaves, and this accumulate together into what we call rules. So let's look at them today. Now, before we go into the circuit rules, very important for you to understand the types of circuit connections that you can do with the components in the circuit. So there are two methods of connection. One is what we call a series connection, and the other is what we call a parallel connection. So just want to let you know, this is a series connection and this is a parallel connection. So in this chapter, we will be looking at how current, potential difference, and resistance are affected by the method of connection. Now, what is a series connection, or what is a series circuit? A series circuit has only one path through which the electric charge or the current can flow. So as you can see in this diagram here, the current flows only through one path, so the current doesn't split up. The components are connected one after the other. So you can see the cell is directly connected to the light bulb, and the light bulb is directly connected to the resistor, and then the whole circuit goes back around to form a closed loop. Okay, so this is what we mean when one component is connected to the other end by end. There's no splitting in the wire or in the flow of the current. We say that these two components are in series with each other. Now let's look at current and what happens to current when you have two components in series. So you have two figures here, figure 1 and figure 2, and I'll explain what they are. So in the above diagram, what you will observe is that the current in figure 2 will be smaller in figure 1. So in figure 1, you have two emitters here. So this is emitter 1, this is emitter 2, and then you have a run resistor here, and this is a cell. In figure 2, you have a cell, you have three more emitters. So this is emitter 3, emitter 4, and emitter 5. And you have two resistors in figure 2. Makes sense that figure 2 has less current. So the current in figure 2 is less, and figure 1 has more current. Why is that? Because figure 2 has more resistor. It has a higher resistance. Figure 1 has only one resistor, therefore its resistance is low. So more current can flow in figure 1. Why is this so? The current in a circuit, so this is kind of like a rule number 0, if you want to think about it like that. The current in a circuit is dependent on the total resistance of the circuit. If the total resistance is higher, then the current flow in the circuit is lower. If the resistance is lower, then the current is higher. The other thing about current in series is that no matter what the value of the current is in the circuits, the emitter can be placed at any part of the circuit because the value of the current will be equal at any part of a series circuit. So what does that mean? So in figure 1, if emitter 1 is measuring with current I1 and emitter 2 is measuring current I2, then I1 is equal to I2. Let's use numbers as example. Let's say the first emitter is measuring a current of 2 amps. Then emitter number 2 will also be measuring the same current, 2 amps as well. If in figure 2, if emitter 3 is measuring I3, emitter 4 is measuring I4, and emitter 5 is measuring I5, so these emitters are measuring their respective currents, and then these three currents will be the same. I3 is equal to I4 is equal to I5. So let's say in this case, let's say emitter 3 measures a current of 5 amps, then the current that is measured in all points of the circuit will be the same. So basically, for a series circuit, the current at all points are the same. So that's the first rule of the series circuit. Now let's look at voltage or potential difference and EMF. How do they behave in the series circuit? So you have figure 3 and figure 4. In figure 3, you have a cell, you have one resistor here, and this resistor is connected to a voltmeter. Okay, so this voltmeter is measuring this resistor here. In figure 4, you have a cell, two resistors, and then this voltmeter V2 is measuring R1, and this voltmeter V3 is measuring R2. In figure 3, the potential difference V1 is measured across R because it is the only component in the circuit. Basically, the potential difference across all resistors in a series circuit will be equal to the value of the EMF. Right, so let's say the EMF, the voltage given by the cell is 6 volts. Therefore, the voltage across this resistor will also be equal 6 volts. This is another thing that you need to know at least. When we think about wires, we just assume that the wires do not have any resistance. It has zero resistance, so the current can flow smoothly in the wire. Even though in real life there's a bit of resistance in the wire because the wire is not perfect, but when it comes to calculations, we just assume there's no resistance. So for figure 4, how do the voltages behave in the series circuit? The EMF is equal to V2 plus V3. So again, if you have an EMF of 6 volts, this EMF here, this voltage here, will be shared among the two other components. So this 6 volt, 3 volts will go to the first resistor, and 3 volt will go to the second resistor. So in other words, if you add the voltages of these two components, you will get back the voltage of the EMF. That's why it's the EMF is equal to V2 plus V3. But if you have only one component, like in the case of figure 3, then the EMF is simply equal to that one component's voltage. Right, so in figure 4, we have the relationship EMF is equal to V2 plus V3. So basically, in a series circuit, the sum of the potential differences across each component is equal to the potential difference across the whole circuit. So that means the voltage here, if you add it with the here, okay, the sum of all the potential difference of each of the component, it will always give you back the EMF of the circuit. Okay, so if you have another resistor here, for example, and if you add that, all of that will give you the EMF. So to summarize, these are the series circuit rules. There are 3 rules. Rule number 1, the current is the same anywhere at every point of the circuit. And rule number 2, the EMF is the sum of all the potential difference for each component of the circuit. Okay, and rule number 3 is something that we'll look at in part 2 of this chapter. And that is the end of the lesson. Thank you for watching.